This is 2018 Usamo problem number 2, and here is a view of this functional equation problem. We would like to find all functions defined on the positive reals, onto the positive reals, such that these functions satisfy this functional equation where x, y, and z are positive, and they satisfy this condition x times y times z equals 1. We can directly begin by dealing with this condition. Just to begin with, this solution is due to Adamov 1, I think, AOPS user. So we can first deal with this condition by using a trick. The following substitution will do the trick. Let x be equal to b over c, y equal to c over a, and z equal to a over b. This substitution is also suggested by Evan Chan as well. It just turns out that you can do that because since you just realize that x times y times z, which is equal to b over c times c over a times a over b, is simply equal to a's cancel, c's cancel, b's cancel, so we have a 1, which is the case. So this substitution basically handles this equality condition, so we're free of this equality condition at this moment. So now let's go ahead and have a look at the starting with the left hand side of this expression. So we would get an equivalent formulation. So let's call our expression, the left hand side at least, star. So this is our functional equation. So left hand side of star is equivalent to the following. So we have the cyclic sum, right? So if you want to use a summation formula, or if you don't, let's just do it the long way. So the left hand side of the star is simply equal to the sum of f of, replace x with b over c plus 1 over y. Y was c over a, so there we have a over c again, plus f of y is c over a plus 1 over z, but so this is just replacing these, so it's b over a plus f of finally z, which is a over b, plus 1 over x, which is c over b. And so that thing is equivalent to, actually this is not a good expression, so the left hand side is equal to, right? So this expression here, we are just replacing with this large expression here, and obviously the left hand side is given, so we are told that it's equal to 1, right? So we can even say that. So and what is the implication? We can further re-express it as a plus b over c plus f of b plus c over a plus f of c plus a over b. We have this cyclic sum. And then at this stage we can do a trick, a further substitution. So this problem we will repeatedly do some substitutions. So go ahead and do the following substitution. Let f of t be equal to g of 1 over t plus 1, or equivalently this would mean that g of s, if you call this inside as s, and so that's equal to let's do it probably here. So if you call 1 over t plus 1 as s and just rearrange, so you would get 1 over s is equal to t plus 1, further implying that t is equal to 1 over s minus 1. So therefore I can replace the t here with that expression, so therefore f of 1 over s minus 1. So therefore what it implies is that we would have an equivalent representation, that namely so we can now rewrite this problem. Actually, let me draw it with a different color. Let's use the red color. So we can re-express this problem in the following way now. So that would imply that this expression is simply equivalent to saying that we have functions g from I claim so from 0 to 1. I guess it's so 2 on to, okay, so why is that? You can just clearly check these. So for instance, if s goes to oh sorry, this one I should say, sorry for that, when s goes to when t goes to 0, right? So when t goes to 0, so we have 1 over 1, 0 plus 1, which is 1, and when t goes to infinity, we have 1 over infinity plus 1 over infinity, which is 0. So therefore our new domain is 0 1. So for the time being, let's omit this range. We will come back to that, so but it will be a specific range such that, okay, so we can be careful at this step. So what we want is that the sum, right? So we have this particular sum. Let's work out this sum. So therefore we can replace each of these. So you can think of them as t here. So we would be plugging in and replace. So that whole thing, so let's open some space here, is equal to g of. So let's be smart here. So we have 1 over b plus, or a plus b I should say rather, 1 over a plus b over c plus 1, right? So plus 1. And we do the same thing 3 times, right? So you can do the other ones as well. But then the good news is when so this would give you the common denominator, therefore would be so this thing would be a c over a plus b plus c, right? And the others will follow as well. So you would have g of b over a plus b plus c, and then plus g of a plus b plus c. But then this gives us the idea of the following thing, such that we would have, if you just assume a plus b plus c being equal to 1, so that would give us such that g of a, because if that's 1, plus g of b plus g of c is simply equal to 1, right? Where a plus b plus c, so I came up with this additional condition, right? Now when this condition is there, because the function g is still positive, defined on the positive, because f is positive valued. If f is positive valued, obviously g will be positive valued. If you are adding 3 positive numbers and the sum is 1, each one will be between the range 0 to 1, right? Does that make sense? So therefore, I hope this part is clear. Well, I was lazy to write this down, but let me just do it just in case some of you guys are confused. So we have a plus b plus c plus g of a over a plus b plus c, and we decided, because it is a plus b plus c for all the denominators, we just decided to set them equal to 1, and as a result we would get this left hand side here, and the sum is still equal to 1. However, now we have this additional condition, a plus b plus c is equal to 1. Wow, so we have an equivalent, so this, or at least this implies this this new functional equation, and I guess simpler problem as well. Now that's what we need to solve. So what we can do here is now we can this is the part which things start getting interesting. We can further make a substitution to get rid of this plus this one business. This one is not attractive, so we'll try to make this 0. So the useful substitution would be, let h of x, now we are coming up with a third function now, be equal to g of. Okay, so with this shifting business, we should be able to work things out, right? Well, yeah, with okay, so with the what will be the domain? Well, first of all, the domain for g was 0 1, and as a result, because we are shifting it by 1 over 3, the domain will shift by minus 1 over 3 in the minus direction, so minus 1/3, and then the 1 minus 1/3 is 2/3. And obviously you need to also work out the range, and range, well, obviously because g ranges from 0 to 1, so therefore subtracting 1/3 from it, the range will be also the same, range of minus 1/3 to 2/3. Now what we are claiming here is that this expression is equivalent valently. So equivalently, this would be the following: h such that it goes from minus 1/3 to 2/3. So in this interval, defined on this interval, such that let me open some space here. Let a be equal to x plus 1/3, b would be y plus 1/3, and c be equal to z plus 1/3. So when you plug them in, you would just realize, so replacing a here, we would get g of x plus 1/3, right? So let me see. Yeah, so let's do it in this space again. So we started with this expression, so we have g of, therefore g of, so replace a with this expression, x plus 1/3 plus, and then the second one, g of y plus 1/3 plus g of z plus 1/3, and this whole thing is equal to 1. Now I will further, noticing my function, subtract 1/3 from each of these. So therefore, if I subtract here minus 1/3, minus 1/3 from the second one, and minus 1/3 from the third one, right? So I'm just subtracting minus 1/3 from the, so 3 times minus 1/3 is minus 1, so I need to subtract minus 1 from the right hand side as well. So therefore this is equivalent to, hey, have a look at this expression. This is simply h of x plus, and this one is simply h of y plus, and that one here is h of z, which is equal to 0. And how about the condition? The condition a plus b plus c equals 1. That has become a plus b plus c equals 1, or let's say 1 equals a plus b plus c, but a replace it with x plus 1/3 plus y plus 1/3 plus z plus 1/3. Obviously, so 1 on the left hand side, 1/3, 1/3, 1/3, 1 on the right hand side. This would imply x plus y plus z is simply equal to 0. Exactly what we needed, right? So therefore, so we have this condition, this functional equation coming up with this condition. So therefore, equivalently, we have this such that h of x plus h of y plus h of z is simply equal to 0, where x plus y plus z is equal to 0. Boom. So therefore, this g expression here, this functional equation question, is equivalent to this simpler problem I claim. And now in the final step, now we can work out to explore the properties of this function. So let's go step by step. So step by step, I will be exploring the features of this function h. So this is a standard functional equation problem. At this step, we can just substitute different numbers. So for instance, if you substitute x, y, and 0, replacing the z with a 0, so that expression will become h of x plus h of y plus h of, replace z with 0. I should have, okay, so let's first plug in 0, 0. Yeah, not a good idea. Okay, let's do 0, 0 so that I get h of 0, right? So therefore, I would have h of 0 plus h of 0 plus, that's a 0. H of 0 is equal to 0, implying 3h of 0 is 0, or simply h of 0 is equal to 0, right? So that's our first observation, so that's important now. Now the second one, like we said earlier, x, y, 0 here, that would give us h of x plus h of y plus h of 0 is simply equal to 0. So obviously I ignored this condition, right? So I need to be careful. So I can't just say x and y, right? So I should rather say, for instance, y and minus y, right? So let me rewrite these conditions. So I can say minus y, y, and 0. So the sum should be 0, right? So I overlooked that condition. So there you go. Okay, so that would imply that h of minus y is equal to minus h of y, suggesting that our function h is odd. So let's do a few more substitution. How about xy and minus x minus y? Obviously they add up to 0 as well. So when I try these, I would get h of x plus h of y plus h of minus x minus y. And this is where I will be using the case that it is odd. So we know this should be equal to 0. But you just realize that this thing is just equal to minus. So that thing is just minus h of x plus y. And I can just rewrite these guys as well, so equivalently. So that would imply that h of x plus h of y is equal to h of x plus y. But now this is beautiful because we have an additive function, right? H is additive. Now I need to make sure all the conditions are satisfied, because I'm very excited, because I can probably it seems that we reduced the problem into a Cauchy type functional equation, right? Where we have a very good idea about the solution. Obviously, the additive Cauchy would be, well, given, assuming, if you watched our earlier videos, assuming that H satisfies some regularity conditions, right? So that the solution, if this is a Cauchy type, Cauchy, well, we are at least suspecting, if that's the case, then h of x would simply, check our videos, you would see that h of x is simply equal to cx. But now, yeah, so for here, to classify this functional equation h as an additive functional equation of the Cauchy type, we need to ensure that h is bounded in a sense. And I hope our study so far has not done any mistake, and it seems that h is bounded, right? So from below, and the range of h. Just wanted to give you one final footnote in case we messed up with our domain of this. What you can also further do is you can check, for instance, x minus 2x as well, which implies that if you plug them in, you would realize that 2h of x plus h of minus 2x, remember our function is odd, so well, that's equal to 0, implying that 2h of x minus 2h of x is equal to no, just take the minus out, not the 2. That was silly. 2, yes. So further implying that h of 2x is equal to 2h of x. So it should be possible to expand the range of the function to accommodate the desired range that we have in mind. But just to wrap things up, so h is a function, so well, h is a function, the Cauchy type function, because well, the functional equation is Cauchy type, it's an additive function, h is additive. As a result, the solution, it's well known to be h of x is equal to cx. And now we can go backwards and substitute things, right? So we have defined h as this, so we can just now substitute into our expression. So replace h with that expression. So let's go ahead and do that. So h of so therefore finally h of x equals well, or you can say the other way around. So cx equals h of x, and h of x can be replaced with g of x plus 1/3 minus 1/3. But then we can move things around, so this would imply cx plus 1/3 is equal to g of x plus 1/3. Now we can substitute x minus 1/3 into x, so therefore we would get c x minus 1/3 c times plus 1/3 equal to, and we do the same thing here, g of x minus 1/3 plus 1/3. That was the whole point of doing this trick, which is just g of x, right? So we are able to express g of x as this expression here. Now finally, one more time, we go all the way up. Remember how f is defined based on the g, so we can substitute, make this following substitution. So plug in, replace x this time with 1 over x plus 1. That would imply that c, so replace, and wherever you see x, just replace it with 1 over x plus 1, so c times minus 1/3 plus 1/3 is equal to g of, replace x with 1 over x plus 1. But hey, this is just f of x, right? So this is just f of x. Whew, so long story short, finally, so this implies therefore f of x is simply equal to c over x plus 1 plus 1 minus c over 3 for all x in the region 0 to infinity. So that's the closed form solution. All functions f that satisfy the given initial functional equation are of this form. The one part that you need to be super careful is the conclusion that I had here. Once we had this additive function, because we are in the reals, we need to make sure we have some regularity conditions, and the regularity conditions that we have used is that and h bounded, right? So the thing that we made use is bounded, so because we have the following range, right? So make sure you keep that in mind as well. And I hope I haven't messed up my bounds. If I did, so you can just correct it on the comment section. Please share your comments. Hope you enjoyed the video, and looking forward to see you guys in the next problem.